Hello class, this is Professor Kamen with Machining 1319. This is part 2 of the welding processes video. In part 1 we talked about fusion welding processes, and now in part 2 we're going to talk about solid state welding processes. Let's go ahead and get started. Okay, so before we talked about fusion welding processes where two pieces of metal were joined together by essentially applying enough heat to melt and fuse the metals together. Okay, so that was a big point. The welding bond was caused by heat. And here's an example. Now, in the solid state welding processes, you're still going to be joining two things and there's still going to be heat involved, but the primary things that are causing the bond are going to be pressure and movement. Okay, so that's a solid welding process. Heat is often generated again, often by friction, but that is not enough to melt and bond the metal. What's causing the bond of the metal is pressure and then movement. Then here you have an example of an ultrasonic welding, and we'll talk about that, I believe, just on the next slide. So one of the first solid state welding processes that we're going to talk about is called ultrasonic welding. And the ultrasonic welding, you have two materials. I'm going to minimize my head a little bit so you can see. Here we go. In ultrasonic welding, you have two materials. First, they're going to be pressed together, and then they're vibrated against each other at frequencies around 75,000 times a second. So that's extremely high frequencies. So you have friction that creates rising temperature, but again, it's not enough to melt them together. What's causing that bond is going to be the pressure and then also the movement. So this is unique because it can be used with both metallic and non-metallic materials, and you see it oftentimes to join plastics together in the automotive industry. Here's a diagram of ultrasonic welding. You have a pneumatic piston that's meant to give that extra pressure there. And then you have a transducer and a converter. All these things are used to kind of get that vibration there that helps to establish that bond. Then down here you have the two lap joints and the horn, and then you have the base applied. That's where the actual joint is applied, where the pressure and the vibration is applied to the metal. So let's look at some videos that give us some applications of this ultrasonic welding process.
How does electric limited ultrasonically weld splices? When making a wiring harness, many times two or more wires need to be spliced together. For years, the only way to do this was the clip and dip method, as shown in the top splice. To make the splice on top, a metal terminal was applied over the wire ends. The splice was then dipped in acid, a cleaning agent, and dip soldered. The newest technology is ultrasonic welding. To make the splice shown on the bottom, an ultrasonic welder was used. This means no terminal, no acid, and no solder. Yet the weld process produces strong, ultra-reliable welds that can be monitored with software to ensure that they are repeatedly accurate. Since the late 90s, ultrasonic welding has become the industry standard and is now required by GM, Ford, Chrysler, Mercedes, and all the major automotive manufacturers. Let's compare the traditional and modern way to splice wires. With the traditional method of splicing, or the clip and dip method, multiple wires were first held together with a metal terminal, as shown here. Then that splice was taken to a dip soldering station. There, the splice was first dipped into a cleaning solution to remove oils and oxidation, which would otherwise hamper the solder from adhering to the splice. Next, the splice was dipped into molten solder, shaken to remove the extra solder, and cooled in a neutralizer. This was the splice method that manufacturers used for years. The negatives to dip soldering is the possible introduction of acid and limited quality control. The splice method used today in automotive wiring harness manufacturing is ultrasonic welding, as shown here. So what is ultrasonic welding? Basically, high-frequency sound or ultrasound causes rapid vibrations within the wires to be welded. vibrations, up to 20,000 times per second, causes the wires to rub against each other. This friction raises the temperature at the wire's surface and sets the condition for the wires to form a molecular bond to one another. The software we use with our ultrasonic welder was custom written for Electric Limited.
Okay, I'm going to stop it right there because the rest is just company-specific information, but that video really kind of told you an application and then how that ultrasonic process worked. All right, so let's continue on. Find my correct space here. Let's look at another video that gives us another application of ultrasonic welding. So you see there's a plastic kind of tube being ultrasonic welded there. That was a very quick and short demonstration, but you can see the ultrasonic welding process there for a plastic tube. So maybe something like a toothpaste tube or something that holds some type of caulk. And so ultrasonic welding is very common in manufacturing industry. Now, another solid-state welding process is friction welding, and there are actually several different types of friction welding processes. So what happens in friction welding is that the heat needed for welding is created by friction at that interface. So you still have a lot of movement, and then you still have a lot of friction going on too, and you also have some pressure taking place as well. And so that heat created by friction and the pressure, they come together to cause a strong bond to form. The first process, friction welding process, is called friction inertia welding. And in friction inertia welding, you have a flywheel that's allowed to kind of freely spin, allowing one workpiece to spin, and the other is essentially jammed into it. Okay, so the other remains stationary as they're forced together. So you have that friction going on as it spins, and then they're forced together. You have the pressure, you have the movement, and that gives you your friction inertia welding. And here's an example of the friction inertia welding process.
How does inertia welding work? Basically, by forcing together pieces to be joined in such a way that rotary motion and pressure are converted into heat, which literally bonds the pieces into one part. Two pieces to be joined are aligned in an inertia welding machine. One piece is held stationary, the other is rotated rapidly on a spindle chuck attached to a flywheel. When the flywheel reaches a predetermined speed, it is disengaged and the freewheeling piece is forced against the stationary piece. Friction between the parts heats the budding surfaces to forging temperature. Just before rotation ceases, the two pieces bond automatically. When the flywheel stops, the weld is complete.
All right. And that is the friction welding process. So remember, that's friction inertia welding. Okay, now linear friction welding is the same thing except you're doing more of a reciprocating action back and forth, but pretty much the same process, just a different type of motion. Now, what's special about this is that it allows you to do parts that are not circular in cross-section.
Low-cost linear friction is an area TWI has been interested in for some time under the LinFric project.
And all of this stuff is obviously machined off afterwards.
Blades to discs in turbine manufacture. They're called blisks. And these are some images of welds made on the new LinFric machine here at Abington. Well, successful welds were achieved in a variety of section combinations. The linear friction team also examined the process with titanium specimens.
All right. Now, the other type of friction welding process is called friction stir welding. This is actually very interesting. So you have a probe that's forced into a joint that's already put together. And what happens is literally the probe spins and mixes the two metals together. And it does that at very, very high forces that exceeds the yield force. And so it really kind of bends the metals together, even though they're still in their solid state. Now, this is done at temperatures around 450 to 500 degrees. It needs lots of force and a very stable setup to take place. So this is a diagram of friction stir welding. Here's your probe. Actually, the probe is right here, and then here's the shoulder. And so this probe underneath is mixing the metals together at this point right here. Here's a video of friction stir welding application process, of an application of the friction stir welding process, rather.
Friction stir welding, or FSW, is a solid-state process by which high-quality and high-strength welds, and potentially difficult to weld
So you see that probe going
possible.
in?
This cutting-edge technology is becoming an increasingly popular choice for manufacturing lightweight transportation structures such as automotive, aerospace, light rail, and marine applications. FSW was developed in the early 1990s by TWI, or the Welding Institute, in the UK, and is considered a green process with no fumes or arc light emitted, nor shielding gas or welding wire consumed. Quebec-based innovation partner CRIC developed this FSW system to utilize the Fennec M900IA robot to perform the welding process.
There you go. So that's very interesting
FSW
there.
requires a large amount of downforce to plunge at the start and maintain tool orientation, so heavy-duty tooling is required to hold the parts in position. The M900IA robot is an ideal solution for this task. Its servo-controlled speed, accuracy, and heavy payload capacity ensure the optimum downforce is applied while producing high-quality welds. The weld's joint is typically configured with two plates in a butt joint configuration, or a through weld stack and a lap joint configuration. The FSW tool provides friction.
All right. Actually, that's one of my favorite friction welding processes. I think that's very interesting how it mixes the metals together like that. And so that is the end of this presentation. Remember, this is part 2 of welding processes, solid state welding processes. Thank you very much.